Well, welcome to Lesson 7 on Unit 2 on applications of proportions. Your learning targets for this lesson are to be able to use proportions to solve problems that involve geometric figures, and also to use those same proportions to solve indirect measurement problems. So first of all, we need to define what we mean by similar figures. In geometry, similar figures have the same shape, but they're not necessarily the same size. So in this picture, I have two triangles, and they have the same shape. They look like they're the same shape, but one is bigger than the other. So properties of similar figures are this. There are two primary properties of similar figures that you need to understand. And the first one is that corresponding angles are congruent. And what I mean by congruent is that they're equal in measure. So for instance, the measure of angle A right here, it corresponds to angle D. Notice we have the way that we represent similar figures is this little symbol right here. And the order of the letters is significant, okay? Since A comes first, it corresponds to D, B corresponds to E, and C corresponds to F. So those are the angles that correspond to each other or are congruent to each other. So we know angle A is congruent to angle D because they're in the same position. They are corresponding. Angle B is congruent or equal to angle E, and angle C is equal to angle F. Now this little m just means the measure of the angle, so those are the symbols and what they mean. You might see equal to or you might see congruent, and the symbol for congruent is an equal sign with a little similar symbol on top of it. That means congruent. So the other property of corresponding or congruent figures, or similar figures, excuse me, is that the corresponding sides, they're not equal, but they are proportional. So what that means is the length of any pair of sides. So I might say side AB would have to correspond to DE. So the ratio of those two sides has to be the same as the ratio of BC to EF, which also has to be the same as the ratio to AC to DF. So that might be a little confusing, so let's go ahead and look at some examples. A scale factor is the ratio of the side length of one figure to the side length of a similar figure. So here we have two triangles that are similar. That's what this symbol means. Triangle ABC is similar to triangle DEF. And so we want to use what's called a scale factor. The scale factor of ABC to DEF, so if I start from ABC and go to DEF, you can look at any two sides. The side AB corresponds to side DE, and if this side is 2 and this side is 4, my scale factor is 5 to 10. I could go 5 to 10, or 2 to 4, or 1 to 2. I could reduce any of those two sides. Now, if I start with DEF, the scale factor of this one to this one is just the opposite. It's 10 to 5 or 2 to 1. So now you understand a little bit about scale factors and similar figures. Let's do some more problems. So here's an example that says every dimension of a 2 by 4 inch rectangle is multiplied by 1.5 to form a similar rectangle. So here we have rectangle A is 2 by 4. Multiply 2 by 1.5 and you get 3. Multiply 4 by 1.5 and you get 6. Okay, so these two rectangles are similar. The question is, how is the ratio of the perimeters related to the ratio of the corresponding sides, and how is the ratio of the areas related to the ratio of the corresponding sides? So first of all, we have to calculate the perimeter and the area. So I've given you the formula for perimeter of a rectangle. If you walk all the way around the rectangle, you'll cover a length, a width, a length, a width, right? So it's 2 lengths plus 2 widths. So for rectangle A, 2 times length, the length is 2 and the width is 4. So 2 times 2 plus 2 times 4. Well, that gives us 4 plus 8, which is 12. The area is the length times the width. Well, in rectangle A, it's 4 times 2, which is just 8. Now we need to calculate the same thing for rectangle B. Twice the length, 2 times 3, plus twice the width, 2 times 6. 2 times 3 is 6, and 2 times 6 is 12. And if you add those together, you get 18. And the area of rectangle B is just 6 times 3, which is 18. So here's the question. Now that we have found that stuff, it says, how is the ratio of the perimeter related to the ratio of the corresponding sides? Well, here's the ratio of the sides. The ratio of the sides is 4 corresponds to 6, which is the same as 2 to 3. So the sides are in the ratio of 2 to 3. Well, let's look at the ratio of the perimeters. Let's see if there's any correlation between the ratio of the two perimeters. So we have 12 to 18, right? So we're going to take rectangle A on top and rectangle B on the bottom. So that's 12 to 18. And if you reduce that by dividing both of those by 6, you get 2 to 3 again. So notice the perimeter is in the same ratio, the same scale as the ratio of the sides. Well, what about the area? Does that also have the same ratio? Let's compare the areas of the two. The area of A was 8 and the area of B was 18. Well, if we divide both of those by 2, we get 4 to 9. And 4 to 9 is not the same as 2 to 3, but it's the same as 2 to 3 squared. Okay, so if we square 2, we get 4. If we square 3, that's 3 times 3, we get 9. So it's the same as 2/3 squared. So the ratio of the perimeters is equal to the ratio of the corresponding sides, and the ratio of the areas is the square of the ratio of the corresponding sides. Kind of interesting. All right, well, let's take a look at a 3-dimensional figure. That was a 2-dimensional rectangle. What happens if we have something like a cylinder? We have cylinder A has a radius, right here, a radius of 4 and a height of 6. And we're going to multiply each of those dimensions by 1/2 to get cylinder B. So half of 4 is 2 and half of 6 is 3. How is the ratio of their volume related to the ratio of the corresponding sides or the corresponding dimensions? Well, the formula for the volume of a cylinder is pi r squared h, where r is the radius and h is the height. So let's plug that in for cylinder A. R in this case is 4, h is 6. So we're going to get pi times 4 squared times 6. Remember, 4 squared is 16, not 8. 4 times 4. So we're going to have 16 times 6, which is 96. And then we have pi in there. Just leave pi in your answer. You don't have to multiply that out. So it's 96 pi units. Cylinder B is pi times 2 squared times 3. 2 squared is 4, and 4 times 3 is 12, so that one gives us 12 pi. Now we have the volume of both cylinders. We want to compare the ratio of the radius, or the radii. This is plural of radius. So we're going to compare 4 to 2, which is the same as 2 to 1. The height is 6 to 3, which is still 2 to 1, which is still 2. So the height and the radius, they have the same ratio. How about the volume? That'll be 96 pi to 12 pi, and the pi's will cancel. So now we have a ratio of 8 to 1. Well, it's not the same, is it? But it is the cube of whatever the ratio of the sides were. So the ratio of the volumes is the cube of the ratio of the corresponding sides or dimensions. So here's a summary for you. If two similar figures have a scale factor of A to B, if this is the ratio of their sides, then their perimeters have the same ratio. Their area has that ratio squared, and their volume is the same ratio to the third power, or cubed. Very, very important that you understand this. So let's go ahead and jump into some practice problems. These two similar figures are similar. Remember, here's the similar symbol. And it says find the measure of angle Q and measure of angle Z. Well, if we just look at this statement, angle Q is the second letter, it corresponds to angle X. So here's angle Q, here's angle X. If X is 60, then Q must also be 60, right? Q, this means congruent, is congruent to angle X, and angle X is 60, so they're both 60. How about angle Z? Angle Z is the last one. It corresponds to angle S. Well, in the picture, here's angle Z right here. Here's angle S. S is 120, so angle Z must also be 120. Find the scale factor of PQRS, this trapezoid, to the second trapezoid. What's the scale factor? Well, to find the scale factor, we need two corresponding sides. We have this side, but we don't have this side. We have this side and we have this side. So those are the two we're going to use. We're going to use SR or RS to ZY or YZ. So we can use any corresponding pair of sides, and we have two. So we're going to say the ratio of the scale factor of PQRS is 8 to WXYZ is 2. So it's 8 to 2, which is the same as 4 to 1. Now we want to use that scale factor to find the length of a side. We want to find how long is QR and how long is WZ. Well, we can use that scale factor. If we look at our figure, we want to find QR, and QR is side A here, okay? QR corresponds to XY. So QR is to XY. Our scale factor is 4 to 1, and XY has a length of 3. So our scale factor is equal to QR to 3. Okay? So now we can cross multiply, and we get QR equals 12. Let's use the same scale factor, which is 4 to 1, right? And we want to find WZ this time. Well, WZ is right here. It corresponds to PS. So we know that PS is 12. So 12 is to WZ as 4 is to 1. And again, we can cross multiply. We would get 4WZ equals 12. And so WZ must be 3 when we divide both sides by 4. Indirect measurement. So this is a really handy thing to be able to use proportions for, is indirect measurement. So here's an example where it says a totem pole casts a shadow of 45 feet long. At the same time, a 6-foot tall man casts a shadow that's 3 feet long. Write and solve a proportion to find the height of the totem pole. So rather than having to find a way to measure this, we can use indirect measurement by using the ratio of the sides. Okay, they form similar triangles. They both have a right angle. Okay, there's a right angle for the height of the person and the height of the totem pole to the ground. So these form similar figures. So what we want to do is to go ahead and write a proportion. So we can say the height of the totem pole is to the height of the man as the length of the shadow to the length of the shadow. So we can say 6 is to X as 3 is to 45. Now the thing to be careful of, if we start with the height of the man on the top, then on the right hand side his shadow has to go on the top. Okay, we couldn't have this flipped over or we'd get the wrong answer. So it has to be the height of the man on top, length of the shadow of the man. Okay, so be consistent there. And then we're going to cross multiply. 3x is equal to 6 times 45. And then dividing by 3 on both sides, we get x equals 90. So x is what we were solving for. So the length of the totem pole is 90 feet. In a scale drawing, a kite is designed so that the length of the tail is 9 centimeters. Okay, so the length of the tail is 9 centimeters. If the scale of the drawing is 1 centimeter to 10 centimeters, what's the length of the actual kite tail? So let's go ahead and figure this out. It said a kite is designed so the length of the tail is 9 centimeters. So we want the tail length of 9 centimeters. And the scale of the drawing is 1 centimeter is 10 centimeters. Okay, so this is the scale to real. So 1 centimeter in a model is 10 centimeters in real life, right? So we want to know what is the length of the actual kite tail. This was the scale of the tail, right? In a scale drawing, a kite is designed. So now we're going to cross multiply. X times 1 is x equals 9 times 10. So x is equal to 90 centimeters. And I'm not sure if I have the answer behind there or not. I don't think I do. Okay, so here's a couple more problems. It says a dartboard is composed of concentric circles. The radius of the smallest inner circle is 1 inch, and with each consecutive circle, the radius increases by an inch. So letter A says, what is the ratio of the radius of the innermost circle to the radius of the outermost circle? So let's take a look at that. So in this innermost circle right here, we have a radius of 1. And if we keep going out, this one has a radius of 2, and then 3, and then 4, and then 5. So the ratio, what is the ratio of the radius of the innermost circle? So it's 1 to 5, right? So that's the ratio of the innermost circle to the outermost circle. What is the ratio of the area of the innermost circle to the area of the outermost circle? Well, the area of a circle is equal to pi r squared. Okay, so the first one, so the innermost circle, its area would be pi times 1 squared, right? Which would be pi. How about the second one, the outermost? Its area would be pi times its radius 5 squared, which is 25 pi. So we want to know what is the ratio of the area of the innermost circle, pi, 1 pi, to 25 pi. And the pi's are going to cancel, right? So when we cancel the pi's, they're gone. What's in the numerator now? What number is there? We canceled pi, but there's still a 1 there for a place marker, so the ratio is 1 to 25. That's going to do it for this lesson. We'll do some practice problems in class. See you next time.